So it's about the projection. Why I need to talk about this? Because in the game part, we have this thing. What does this mean? Means we have to keep ourselves in the game. If due to some reason this step push us away outside the game, that means we break the rule. So in other words, what's the point of this thing? Is to keep ourselves in the game, because this one does not make sure this is the case, right? It's possible we go outside, right? So we need this. So I need to now talk about this, okay? So again, this is projection. That means start with letter P. In Greek, P is pi, so that's why we have this. Or we write PRJ, okay? Basically means projecting a point x to a ZS, and this a lot of things, okay? I don't have time to talk about this so much. You can have a look or just listen to this. So this is called projection onto simplex. Suppose D is 3, X is X, Y, Z, okay? 3D, I have 3D, okay? Then I have this. What the heck is this? This will mean X plus Y plus Z smaller than 1. What the heck is this? X larger than 0, Y larger than 0, Z larger than 0. So I have this 4 line. This is in this direction. What does it mean? This means Y larger than 0. In this direction, what does it mean? It means X larger than 0, because it's X. In this direction, what does it mean? It means Z larger than 0, okay? So in other words, X, Y, Z larger than 0 means I'm in yellow box. So this means yellow box, okay? Now I have X, Y, Z smaller than 1. What the heck is it? Well, but if I put Z equal to 0, then I have X, Y smaller than 1. So first find the Y line X, Y equal 1. So that means X is 1, Y is 1. Then I have line drawn here. This is X plus Y equal 1. And now smaller 1, right? That means this way. Okay, because 0, 0 is also 0 plus 0 smaller than 1. So therefore, this is the line. And then what happens if I put X equals 0? I have Y, Z smaller than 1. Y, Z smaller than 1, that means this line. In the end, X, Z smaller than 1, it means this line. And that means what? Yellow give me the box, red give me this triangle. So in the end, what the heck I have? This region, including the inside. It means if I turn this a little bit, I will get okay, I try to draw this way. Okay, you can see it. If I turn this a little bit, then I will have this. This thing is the simplex, okay? 3-dimensional simplex, okay? So what the heck is this thing? You can think of portfolio 1, portfolio 2, portfolio 3, 3 portfolio, D is 3, okay? Now we have $100. You now go to 1, 2, 3. We know money cannot be negative in investment. So if you go to number 1, you have to pay some money in X money. You have to be larger than 0. If you go some money to number 2, you have to pay Y money larger than 0. If you go to number 3, you have to pay Z money. It has to be larger than 0. So this is what? The yellow box, right? The yellow box. Okay. And then what? You have only 100 money. And I now assume you cannot borrow money. No borrow money, okay? Then if there's no borrow money, then X plus Y plus Z is larger, it's smaller than total money, 100, okay? And let's ignore 100. Let's say it's 1. Then what the heck is that? This is the triangle, okay? So what the heck? This means what? This means suppose I have to invest in 3 portfolio, X, Y, Z. Then this side triangle means what? This triangle means what is my decision? So I will have a X, Y, Z coordinate in the 3D space in R3. Now I don't want any R3. Because this allows me to have a number that like 999999999 impossible. I don't have that many money. So I will have some number X, Y, Z that has to be in triangle 3 or simplex 3. This means I can do some decision within this shape. That means I have to inside this triangle or this simplex or this pyramid. Inside this pyramid or simplex means I am not breaking the money larger than 0 and I'm not borrowing money. I have some 100. I just distribute 100 in X, Y, Z. And also, remember, S smaller than 1, it's not must be 1. So it's portable. This 100, I go in 50 to X and then 0, 0. So I only spend 50 and Y, Z I don't spend. It's still okay. So the rule is I have to spend larger than 0 and at most 100. It does not mean I have to spend everything, right? So this is the same as we go back to the rule. The rule is, yeah, this is the rule. Then the question is, how the heck after we do some X update, X is our decision, it's our objective variable, it's our optimization variable. That means we do something to minimize something. So we can move outside the simplex. That means breaking the rule. Then we need to project it back, right? So we need to project it back. So that means what? I have a number, X is a vector. The projection will say, please solve this optimization problem. What the heck is this optimization problem? So the detail is this slide. I don't have time to talk about it, but now I explain it very quickly. So basically it's this. I have 3D. The feasible set is this yellow triangle, okay? Now let's say I have a point X. What is this projection? Projection on triangle of this X is to solve the what? Is to solve V in triangle such that V minus X is smallest. This is distance between V and X. So I'm saying among all the points inside the triangle, this means all the points inside the triangle, find the V that is closest to X. If I draw a picture, Is this point closer to x? Well, it is closer to x if this distance is the shortest among all possible green to red. Okay, then that means what? I just need to find the shortest line between green and red. Then that point is the green. That's the meaning. So in other words, what is projection? It is projecting a point onto a point here. Then how do I actually solve it? Is this. What the heck is it? This is L2 norm ball. So L2 norm, what's L2 norm? It's a Pythagoras theorem, it's a norm ball. So therefore, what does this mean? This means everything, this thing have a radius r. This means a bunch of vector y, that y minus x, the radius, the distance is r, right? This is equation of circle or sphere. So that means everything here is a bunch of y. These are y, 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 y. They are all y. They all distance to this x is r away. Then what I'm going to do? Well, I just need to what? Grow this red ball. I grow a bigger, and I grow bigger. Eventually, it will be a moment. So suppose I grow this big. This is 3D picture. Please don't bear with me. And this thing touched the yellow. At this moment, this is the distance that is shortest, and this point is the v. Okay. So then that's the idea. I want to find a point projecting of this x into this triangle. It's actually find this ball. When the ball touches the plane, this is the solution at the cross point. So this is the thing. I want to solve this optimization. This is also an optimization problem. And D is defined as this: every value larger than 0, some less than 1. This optimization problem has no simple closed form. That is, what is the projection of a point inside a triangle? You don't know the expression. Actually, this is a solution. I will talk about it later. So this is no simple closed form solution. Then, if I give you an arbitrary x, can you find a solution? Yes, you have to do Lagrangian multiplier, and this will be the solution. That is, the solution of this thing will be this funny function. What's the funny function? It's everything in x minus a number multiplied 1. So what the heck is that? That is, I have x, y, z. This is my input. The solution, that means projecting x to a triangle, will be everything is minus mu, mu, mu. Okay? This is, and then what? Everything, if this is negative, go to 0. Positive, keep the value. This will be the closed form solution of this projection. Then what the heck is this mu? What the heck is this mu? This mu has to be the mu such that this is true. What the heck? I'm now going to explain this. So let me recap, where are we? So I'm now going to talk about the technical detail on projection operator. The reason is that because we need to have a projection inside a set. What's the meaning? The projection here is mean we have to keep ourselves inside the game. Otherwise, we are not following the rule. That means we fail. So we need to make sure we follow the rule. So that's why we need projection. And projection is not simple. You see so many slides I have. Yes, projection is so hard that it worth a PhD to study. Yes, not joking. So let me now go to projection. That is this file. So I just go to this file, explain. This file is not long. That is, how do you project onto a simplex? How do you project? This is simplex. So what is simplex? So simplex is the following. So number one, first, this is inner product. What's that? This means x dot 1. Okay? And then I'm now using r dimension. It doesn't matter. So usually you have x inner product equals some number. Let's say a. Now we don't care what the heck is a. We just assume a is 1. Okay? Now we have this. Now we have this. And what the heck is this? This is what? Larger than 0. So let me repeat. I have 3D. Let's say 3D, 3-dimensional space. Larger than 0 means I am in this green box. Okay? Because everybody have to be larger than 0. This thing means I have a triangle here. Okay? And in the end, it means I must be inside a triangle. Okay? Something like that. So now, what the heck is this? This is a set, right? Is this a convex set? The answer is yes. So how do we tell a set is convex? Last time, a set is convex is I have a point UV and the line between is always U inside S. This is convex set. Now I have a triangle, this delta thing. Is it true? Yeah, let's try. This is I have a point. Okay, now this is X, this is Y. So this thing is what? This thing is convex combination between X and Y. So lambda X plus 1 minus lambda Y for any lambda. That means if this is half, I can have half X plus half Y, right? And I can have 0.x, 0.9Y, right? Or I can have 1x plus 0y, right? As long as this number are 0 and 1, then this is this, right? Then this is exactly the expression in the triangle, right? The triangle is I have this. Then, okay, this thing, what the heck is x inner product 1 times lambda? So this term, and then this term on the top is this term. So this on top is 1 minus lambda, 1 minus lambda. Y inner product 1, y inner product 1. Okay, I have this. And now what's next? Well, Because both x and y are inside the triangle, so that means they have to be equal 1. So this whole thing is a, this whole thing is a, so I have this, and then it's just a. So that means what? They are inside the delta. That means it's inside the triangle. So therefore, this is a convex set. And now, if I have convex set, then good news is this thing have a solution, and it's unique. Now let's talk about how do we solve this. So this thing is actually very hard to solve. Why? Because this relates to something called projection onto convex set. What's that? Look back here, we have two pieces, one pieces and two pieces. Okay, pieces 1 and pieces 2. So actually I can say it's a set 1 and this is set 2, right? Pieces 1 is dot product is 1, pieces 2 is everybody larger than 0. This had nothing to do saying it's larger than 0. Actually, this one is unit simplex in 3D. That means it will be the unit pyramid. Okay, try to imagine. Okay, how right? Okay, yeah, something like this. Okay, so that means the two pyramid. Okay, this is the unit simplex. Okay, so because I have this C2, this is the C1, and I have C2. C1 and C2 intersect each other, will cut away only the positive part. That means I only have this part. That's why I get the triangle. Okay, so this is the correct picture. Now go back to here. How do you project into this? Classical way to project into this is you do, that means you want to project into C1 and C2. How do you do that? Is do this. It's project to C1 and then project to C2 and then project to C1 and then project to C2 and then project to C1 and then project to C2 and blah 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 blah. So what does it mean? Imagine this is C1. Imagine this is C2, this is C1 and C2, right? So how do you go inside yellow? If I have a point here, I project to C1, and then project to C2, and then project to C1, and then project to C2, and then project to C1, and then project to C2, and then project to C1. Now you see, the issue is, this may take forever. That's the reason why this problem is hard. In the end, it will be related to the angle between the C1 and C2. Think about this. If my C1 is this region, and my C2 is this region, suppose I have an angle here, very small. Now, actually 104x or 5x, I don't remember, von Neumann proved the following. I have a point here. I want to go into the intersection between C1 and C2, so probably here. I want to go here. So if you project to C1, you will first go to here, right? And then now you're here. And then you project to C2, now you go here. And then you project to C1, go to here. And then project to C2, go to here. Now you see, this is forever. So you will have to do this. And now you see, even this simple two line, just C1, C2, it can take 8,000 iterations just to go here. So in general sense, projection onto convex set is very slow, very slow. So if you do this until it converges, it's expensive. So projection is never a simple problem. Don't underestimate it, okay? So how do we project then? Now I have this problem again. I have a y, so I have to project y to x. So y is the fixed point given, okay? Now I write everything as an optimization problem. So x is my variable. So now I have the C2, C1, right? This is C1, this is C2, right? Okay, now I have to solve it. And because I don't want to do projection by C1, C2, it's stupid. So I have to do something called duality or Lagrangian multiplier. So that means I'm going to do the following. So first, I have two things. So I have two constraints. I call this P, problem P, two constraints, red and blue, red and blue. So inequality and equality. So now I'm going to do the following. I'm going to put this part into here. This is not come from me. This comes from Lagrange 200 years ago. So I put this here. This is what? This is a number. X minus y 2 norm. What the heck is this? This box is inner product equal 1. It's also a number. So I can have number, add number, fine. And I need to add a scalar. So I put a scalar, mu here. So what I'm going to do is, I want x transpose 1 is 1. Now I consider minus 1. If this thing is 0, it's the same as it is equal, right? So I want this to add inside my objective function. So I have this. This is the inner product minus 1 over mu. Okay. So now I have this thing. This is my P. No longer have P. I have something called L. Lagrangian. This was Lagrangian. And this is not, this is ignoring the red. So it's called partial Lagrangian. So I don't care about red for a moment. So I have this. And this mu is called Lagrangian multiplier. So it as a number. We need to decide. Usually, if I don't care about the mu and I fix this mu, let's say I fix it to 5,000, then this is called a penalty. Basically what I mean, look at this expression. It says, please make this small. Now suppose I have this. It will mean what? Please make this small and also make this small, right? Make this small clear. Find a y and x that is close to each other. Make this small means what? Make this small means I want this, right? I want this to be true. So therefore, penalize the constraint is a way to remove the constraint if this is a good number. Okay, so we now want to talk about how do we solve this thing, and this is called partial. Now So how do we go and do that? We now have two things. Instead of x, we now have mu. Previously here, we only have x, right? So this is a problem on x. Now I have x to x and mu. Actually, I make my problem harder because now I have bigger. So, but I use a bigger problem so that I don't need to worry about the blue anymore. So this is the idea. I make my problem harder, but I now can deal with constraint. Now I move the blue inside the L, so I have this. And originally I want to mean x, right? So mean x stay there. And don't forget I have the red part. So I didn't put the red part inside my function. So my red part stay. Red part is x larger than 0, so x larger than 0 is there, is here. So my red part is x larger than 0. Now I have my new thing called mu. What the heck is that? Go back to here. What the heck is this thing meaning? So this means what? This means, so what does yellow mean? Yellow means please x dot product with 1 is 1. What the heck is this mean? Means the difference between x dot 1 and 1, right? This is the difference between x dot 1 and 1, right? If this is false, what does it mean? If this is false, that means x dot 1 is not 1, right? X dot 1 is not 1, what does it mean? It means x dot 1 minus 1 is not 0, right? Right? If x dot 1 minus 1 is not 0, what does it mean? It means this thing is some number, right? Some number, right? So it can either be x dot 1 larger than 1 or x dot 1 smaller than 1, right? Doesn't matter for a moment because I will have a mu here. So suppose I have this, what does it mean? It means, oh, my x is too big because I want x dot 1 equal 1. Now my x is too big. Then if I make the whole thing small, then it will lead to here, right? What about this one? This one means x dot 1 smaller than 1. Oh, my x is too small, so my x must be bigger, right? My x bigger, then it will go back to here, right? So this is the two cases. Now, getting bigger or smaller will be decided by this mu. So this mu means I have to add a number, mu here, to tell how important to make sure this is not violated leading to yellow. So this mu need to change. I cannot fix, can I put this is 0? No, right? If I put mu is 0, this term disappear. It's basically the same as I ignore the yellow, which is wrong. And secondly, can I put this mu is infinity? If I put this mu is infinity, basically means this one I don't care. I just fit this one, which is also wrong. So that means there will be a magic mu, somehow balance between this term and this term such that this is minimized and at the same time this term is fulfilling the yellow. So what I want to do is to find the largest possible this such that what I said is true. So mu must be as big as I want. So I'm now having a double optimization problem. What's a double? Previously I only have red. Now I have mu. What's mu? X and mu is two variable. And now I want x small, mu big. This is called saddle point problem. So what is saddle point? So this is abstract. So for example, think about this is an x space. Originally, I only have x minimized. So for example, I have a function like this. That means I want to go here. Okay. Now, because of this, I no longer have x space. I also have a mu space. So now I have a what? I have a surface. Okay. Moving here is x. Moving here is mu. Now, what I want in x direction is min, but I want mu direction is max. So what does it look like? If I have both is x min, y, and mu min, then I will have this way is like this, and this way looks like this, right? Because this means this is smallest, this is smallest. That means in the here, it will look like a cup, right? Because if you stand here, view in this way, this shadow is this shape. And if you stand here, view this way, this shadow is this shape. But now the funny thing is, now mu is max, because x is min, mu is max. So that means I will have something in the middle. If you look this way, the shadow looks like this. If you stand here, look this way, the shadow looks like this. So what is it? This surface is called a saddle point. This, and then it's actually is a Pringle chips. Okay, so what's that? So in this way, if you look here, this is in the x direction, it's a U shape. But if you look here, it's a Pringle, so it is like this. Okay, this, right? So it's up. So you are trying to find a point here. It's like a chips that in one way viewing it is going down, in another way viewing it is going up, and this is called a saddle point. So that's the thing. Lagrangian optimization is always chips and find a saddle point. So I'm going to solve this mu such that this is smallest on x, largest on mu. Okay, these are details, not important. Okay, let's talk about it. I have the red. Let's talk about the x. So this is the whole thing, right? What's the whole thing? I have this thing and I put the yellow inside the thing here, then it gives me this, right? This is the whole L, and I want x min mu max. So x min mu max, let's look at x first. This is the x, and the red is because I have the red in the very beginning, right? So now I have this part. So how do I solve it? Well, first, everything on mu is not important because I'm now talking about x, so mu is constant. So this thing, what's that? This is mu x inner product 1 and minus mu, right? Well, mu have nothing to do on x, so I don't care. So that's why I don't care. This one I don't care. So I get this one. Okay? And I can put the mu inside. So I get this. Okay, so I get this. Then what? Now I have this. So what the heck is this? Well, this thing is simple, right? X minus y 2 norm square is what? Is I have a vector x, x1, x2, blah, 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 minus y1, y2, blah, 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 each of them squared. That means it's this part, right? And then what about this part? This part on the top is what? Summation dot product, right? x1 mu 1. This vector, everybody is 1, right? So basically it's just a bunch of x times mu. So in the end, it's just summation this. And since this is a coefficient, I can move it out. So this gives me this, right? So in the end, I have this thing. And the summation side I put out. So I have this thing. So what the heck is this thing? This is a bunch of small l. So this is a big L. Big L is a bunch of small l add together. So that means if each of the small l is minimized, then the big L is minimized. So I have to minimize the small l. And the small l is very simple. Come on, it's high school. Okay, it's a quadratic function with a mu. So how do I minimize the small l? Well, it's very simple. You just look at this expression here. So, okay, this is detail. How do you solve this thing? Okay, high school. X squared minus 2xy plus y squared plus mu x, right? And then what? 2y minus mu x plus y squared, right? So in the end, okay, you remember ax squared plus bx plus c, there's some b minus square root blah 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 thing, right? Then that thing will relate to the b, right? So therefore, the b thing is the y minus mu is the key point. Because of time, I will skip. So you got the idea. The solution is the yi minus mu. If it is larger than 0, then you get it. If it is smaller than 0, then you replace it with 0. The basic answer is this: because you have a quadratic, you can solve for the bottom, and you have a constraint that is x larger than 0, right? Suppose this is the bottom, and this is within this region, then you take this point. And suppose the bottom is here, but you allow only this region, then what is the smallest y value? This point, right? Then you take 0. So that's why you have this. And therefore, each of them is this. The whole vector is just y minus mu 1. This is exactly why if I project a vector, I have a vector minus a constant vector 1 with a mu, and then truncate everything negative to 0. This is the projection onto the simplex. Then now the question is, what the heck is this mu? So we need to find mu. Recall, I have constraint. What's the constraint? Let me go back to the very beginning. What's the set we have? Inner product is A, x larger than 0. Okay, so now I have x equal to something related to mu, right? So what I can do is, this is the solution. I can put everything here, replace it by this thing, right? So if I replace this, okay, what I will have is this. Okay, this is A. I made a mistake. Okay, this is A. This is A. Okay. So if I put this thing here, I will get this. Well, this is basically inner product of x and 1. So that means summation of x is A, right? If I put x inside this thing here, then this thing becomes summation of each of them is A, right? And now if I put this thing inside here, it means what? It means this thing always larger than 0, right? But this bracket plus already is always true, so I don't care. So I will have now this thing. So what does it mean? It means, well, the mu is a funny number that if I solve this piecewise linear equation, then I will solve the Lagrangian multiplier. So what the heck is this? Let's think about a two-dimensional example. So suppose I have y1, y2 is, let's say 1, 2, okay? And then, so what the heck is this? This basically is saying max 0, 1 minus mu plus max 0, 2 minus mu equal, let's say h1. Okay, that means what? I have to solve this nonlinear equation. Okay, what the heck is this? So let's look at it one by one. What the heck is 1 minus mu thing? So now I have a mu axis. Okay, and then this is the y value. What is 1 minus mu? This, right? First of all, okay, everybody knows this is negative mu, right? And then 1 minus mu means move 1 unit upward. So you have this. Okay, this is 1 minus mu. Then what about this? This is 2 minus mu. So probably something like this, right? So now what does it mean? So now I have these two add up together, but also I have max, right? It cannot be 0, right? So that means what? That means this is 1 minus mu. What about this one? It will be cannot touch 0, so I will have. Oh, let me change color. So it means this. This is this, right? What about this one? Well, same. but taller. Okay. So now if I add them up, so I will have 2 minus mu. This is 2 minus mu, right? Okay, let me change color. In blue. Okay, 2 minus mu. Let's say like this. So this is the blue part. This is the red part. What about the whole thing? The whole thing will be that both of them add up, right? The both thing will be, let me draw 1, this is 2. So before 1, both of them add them up, so it will be taller. And then after this part is 0, I only have this left, so I will have this. So therefore, what is this line look like? This funny equation looks like okay, something like this. Let me draw better. So it's a broken piecewise graph. Then now, this is what? This is the y minus mu summation equal a. What the heck is a? This is a. So what the heck is the solution of this? Is to find this point such that it crosses. That's the solution. How do you solve this kind of funny expression? Well, you have to do stupid computer science searching. So what's that? You now have one pieces L1, second pieces L2, third pieces L3, fourth pieces L4, and so on. So suppose you have n pieces. That means you have L1, L2, blah, 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 up to Ln. Each pieces you can find a breakpoint, okay, the starting point, ending point. So you have the AB, AB, AB. So this is the A1, B1, this is A2, B2, and so on, right? You have a bunch of A. Then what do you do? For each of the pieces, you know the A and B, you know the slope, you know the definition of lines, then you just check, is that particular line equal A, crossing A? So in other words, how do you solve this funny expression? You sort all the AB, and then you check manually whether or not that particular line cross the particular A. And sorting, okay, I don't know, do you know sorting? The cost is n log n. So therefore, this thing, how to solve it? The cost is n log n. And this, therefore, in the end, now solving this thing is a n log n cost. So that means what? That means, in general, how do I solve this thing? Is to sort the y. Now you have abort all the y. And now you find a k which is the largest integer. That this is true. This is true means you have crossing, you have some line cross this point. And once you find that, you will get the answer. So basically that's the idea. These are details. I don't want to talk about it. Basically the idea is, you understand what I'm doing in this picture, you understand the idea. Because this thing is a piecewise function, so you have to sort it piecewise. So in summary, what's the heck? How do you solve a projection into simplex? It turns out it's not simple at all. You first have to form a Lagrangian, and then you have to solve the thresholding. What's the thresholding? The thresholding is this thing. This is called thresholding. And to find the threshold, that means the magic number mu, you need to do a sorting on the piecewise linear function, which the cost is n log n. And with this in mind, now I can go back to projection in the here. So how do we going to do in the projection? Well, it's the same. We are going to solve this. So if I have a point in the game, let me go back. I have a point in the two-player game. I will first do a gradient descent, and then I will project it back. Suppose my projection step is to project into simplex. This simplex means I'm doing what? I'm doing what? A D portfolio convex combination. That means I have to, within three thing, I have to select something among the three, cannot go outside the three option. Then this refers to projection onto three-dimensional simplex. And to solve a three-dimensional simplex, I have to solve this. And to find a mu, the cost will be n log n, which is 3 log 3. That means it's very cheap.